Ladies and gentlemen, I'll take your attention. Thank you for joining this graveyard shift after that. I'm not sure which is worse, fallen to Austin, fallen to everyone's looking to go and have some heat. So this panel is titled IEEE and new Wi-Fi standards, and I'll do a quick introduction of the panelists. I must start with two apologies. Greg Locke from Internet Solutions is mad to attend today. He called ill this morning. He sent his apologies. And then we were scheduled to have Stephen McCann on the line, but due to a shift in our schedule now, we have Adrian Stevenson on the line. And Adrian, can you hear us? Can you guys hear Adrian?
Struggling.
Okay. So that's good. Yeah, we can hear you. So we'll try our best to get to hear Adrian. I'm going to quickly do an introduction of the rest of the panels and then we'll come back to you, Adrian. You're going to have to introduce yourself. I don't obviously have been given anything about you. I'm going to start at the far end with William Stuckey. He programmed his first computer in 1972 and he built his first underground fiber optic and wireless networks in 1997. He started an ISP called ZANet in 1996 and has gained a number of South African firsts. He has consulted in internet-related matters, including policy, telecommunication, and wireless. He is the past chair of ISP, the past chair of and also past treasurer of ISPO. Many of you will know William as the councillor for CASA in the last year. And I think I like this sentence a lot about you, William. He's an agitator and a public speaker for telecommunications liberalisation in Africa.
That was the boring version. I did give him a
And he has trained others on ISPO and IXP formation, ISP entrepreneurship. He knows how to configure a bibliothèque. The networking is the routing, so I think it's very relevant to our discussion today. Then next to William, we have Kervin Pillay, is the co-founder and CEO of Avail, who specialize in providing network functions, virtualization, software-defined networking, and WebRTC solutions to the emerging markets. Kervin is a technologist that pioneers new technology by actively contributing to the IEEE and 3GPP standard bodies spanning the real-time communication protocols and system spheres. He has worked in telecommunications for 14 years, spanning mobile network operators, fixed network operators, and internet service providers across Europe, Africa, and North America. Thank you for joining us. And then to my direct next to me is Adil Asim. Adil is a system engineer at Cisco Systems. And he previously worked at Bytes, so as a system engineer. That's about as much as I know of you. So I must apologize, Adil, who also joined us in a replacement for one of the other gentlemen from Cisco. So, good. Adrian, can you hear us? Will will you give us a quick introduction to yourself?
Yes, of course. My name is Adrian Stevens. I'm employed by Intel Corporation, and I'm also actually 802.11 working group chair and technical editor. I've worked in standards for 10 plus years. Before that, I worked in wireless products for 10 plus years.
Perfect, thank you. So, I have the privilege of having done a little bit of homework and read up on the IEEE and some new Wi-Fi standards. I must confess that I myself am not a Wi-Fi expert. I am more of an RF engineer. But I did some interesting reading, and I wanted to read this to you and to get kind of the discussion going from there. So I found on the web a study by a group called the Wireless 2020 study. It was this white paper was written up by Randall Schwartz and Magnus Johansson in March of 2012. Now, to summarize what they've done, they went and building a business case for carrier Wi-Fi offload in the city of New York and the city of San Diego. And to summarize what their findings are, they said for a very dense urban market such as New York City, a positive return on investment is achieved with as little as 20% geographical coverage and an access point density of 24 access points per square kilometer. The maximum savings in the total cost of ownership occurred at 100% coverage, which requires a density of 42 access points per square kilometer. Interestingly enough, by deploying the Wi-Fi offload network at this optimal balance between coverage and density, an operator could reduce the number of macro LTE capacity sites from 1,879 sites to a mere 432 sites, a saving of 1,447 LTE sites in that urban environment. In financial terms, this translates into a cumulative total cost of ownership savings of over $250 million and a significant 7.2% reduction in the total cost of ownership over 10 years. In this case, an operator has greater flexibility in implementing a Wi-Fi offload network because of the positive TCO, as long as the total OPEX per access point is less than $40 a month. When the monthly OPEX per access point exceeds $100 per month, the business case becomes challenging. Now, this was the finding of that. It is quite a long paper, but I thought the summary was probably a good kick-off into discussing some of the technologies that we're seeing, and in particular the Wi-Fi offloading scenario. So the first question that comes to my mind, gentlemen, is congestion. Surely with 24 to 42 access points per square kilometer in an urban environment, will that not create spectrum congestion? Can you take it?
I can take a crack at that. I've just gone back from the US and I spent a fair amount of time in New York. And I can tell you that you're not going to get the same types of APs in every single place. So for example, you're going to get a mix of 2.4, 5 gigahertz, 60 gigahertz. You're going to get a massive mix of types of APs to support the different types of workloads that are going on. So that's the first thing. The second thing is they are very good at doing frequency planning. So, and guys that come from a mobile background will know if you get your frequency planning right, you can have twice as many APs as that and still not have congestion. So it very much depends on what the workloads are and what people are doing. A lot of the time it's downloading email. You don't need massive bandwidth to download email. In fact, you don't need massive bandwidth to do Internet of Things that's using MQTT and CoAP. It's kilobits. It's not megabits. So I think what you're gonna find is that you're gonna get the range of ABGN, AC, AX all the way through, but not everybody is going to be using the same technology at the same time. And that's the challenge to move people around when it makes sense.
And I think from what we've seen from large deployments, so we're talking things like 8,000 people in a single venue, Mobile World Congress, that just happened last week. When we look about that scale, then we see things like shift to 5 gigahertz become more important. So 2.4 gigahertz really falling on the back foot because of the limited amount of channel availability and things like 5G taking over, becoming the new standards within AC. So we'll start seeing a change of behavior from client devices that get developed. So if you look at from this year onwards, it's 50% more, or 60 to 70% of devices will be AC compatible. So when you're looking at that type of dense environment, you need the extra channels that are available in 5 gigabits to do that type of channel planning and get it right. 2.4 is just not sustainable.
It may be true that most people will be using it for email, but that's not the biggest use of data. We're already past the level where 70% of mobile data is effectively used. So we can certainly expect a great deal of traffic flow. 42 APs per square kilometre works out about 1 every 300 metres. If you are only using 2.4, and you're bearing in mind that everyone's got 2.4, that their own internal 2.4 Wi-Fi in their house or their flat or whatever, you would really struggle to deal with frequency congestion with 2.4. But if you're using the 5 gig band, Kevin quite correctly said, designing your spectrum usage isn't very hard. There are people who know how to do it, and it just needs to be done properly. And then the last point is, Jens, you said each area. It doesn't need to be each area. Why wouldn't they use sharing facilities?
Yes. Jumped ahead on one of my questions.
Isn't that question each area?
Oh, yes, you're right. Actually, I did say that. So yeah, you're right. So each MNO they could be sharing the AP assuming that there's only a limited number of SSIDs that are required to do that.
There's an infinite number of
SSIDs.
yes, it's a character story.
True, but not the access points can the access points can only handle a certain amount of SSIDs, otherwise you can.
Yeah, I think we're past that point now, where there's going to be a limitation, especially in access points, AC access points, and going forward. The number of access points are not going to be limited, or the number of SSIDs rather. What the vendors are doing now, like we correctly said, is let's just deploy one access point and we'll put all of the SSIDs on it. In fact, it's the same frequency, it's just a different SSID. So then it becomes a different problem inside. So it's not so much a problem anymore of exhausting the number of SSIDs. I think we're wrong.
Adrian, do you have any comments on that?
On this topic, I would say just generally that I think many of the questions that you're raising are very interesting ones, but they do not relate to standards, they relate to close to the Wi-Fi lines. So I would be interested to hear what your plans were to engage with the Wi-Fi lines to answer some of these questions.
The answers to that?
Yeah, so I think from Cisco's point of view, we work very closely with IEEE as well as the Wi-Fi lines. So when it comes down to things like 802.11ac, 802.11ab, so white space and lower bands, that is where we monitor to see what's happening in the industry and how long it takes to adopt those type of standards, and things like AX. So as far as I know, we're getting ready to do to jump into the test beds now for AC Wave 2, and I think from a Wi-Fi line certification perspective, we will introducing and we know the consumer is the device. So when the consumer devices are manufactured, there needs to be a wireless anchor in the back end, and similar to what we've seen with 802.11n, there were some pretty standard devices once the stack was ratified. So we work in a similar fashion. We follow what the Wi-Fi Alliance is doing. We have products certified in conjunction with that, and also to match consumer demand. So I think as part of the vendors, not just Cisco, the integration into the Wi-Fi Alliance is what we bring us down to consumer enterprises and capabilities.
One of the things that most students in there is addressing is high efficiency. So, and this comes from people observing that the existing protocols are not particularly good when you get really dense deployments. And so they, provided they do their job well, and it's still very early days of designing technology that will contain mechanisms explicitly for allowing creation of very dense networks of users. There will be all kinds of multiplexing, both spatial and in frequency. And actually what that means also is that you're, rather than talking at a high rate for short periods of time, the emphasis is now moving towards talking for a longer period of time over a narrow channel and sharing that activity with multiple stations. And that's good for a number of reasons, power saving and range amongst them. So I think the possibilities are very exciting. What the industry actually ends up with is still a big TBD, but we're talking about a number of years in the future before you see any of this kit.
Any comments on that from the audience?
So you read a summary of a report related to a network in a city that is non-existent in Africa. The topography and the geography of South Africa and Africa is non-existent anywhere else in the world. We don't have these cities that live on top of each other where those networks work and are viable from a business point of view as well as a technology point of view. So how are we going to take these standards that are amazing and develop provide high capacity in a rather expansive geography that we live in here in South Africa?
So I think some of the other standards do address that. So when we look at Wi-Fi at its 11 in AC, we address smaller spaces with more dense environments. And I think very similarly, we have those types of dense areas as well as a lot more sparse areas, right? So we make use of a very similar high-dense Wi-Fi that you would find in smart cities like Barcelona, etc. When it comes to the open space, there's a lot of initiatives, things like AH, TV white space, where you have lower spectrum, lower bandwidth, a lot more coverage. Now, the adoption on that is a different story. That's why these standards fail within IEEE, or they slow down significantly. So you have client devices that are this additional chipset. It's expensive to manufacture because no one wants to get into the space. And ultimately it comes down to IEEE and Wi-Fi lines displays. If the vendors and manufacturers are invested in money into those spaces to develop hardware, so you're going to develop the chipset for the consumer side, you're going to develop the wireless AP or radio side. If there's no investment in that, if there's little benefit that those vendors get out of it, it doesn't become feasible for them to manufacture or produce such a product.
We get back to what we're sitting with as society that exists in South Africa, and that there's a huge divide between these places that have the money to invest in that and the places that don't.
So that is why, that is how we come to the balance of having relatively AC. And as we see within, it becomes more commoditized, it becomes cheaper, it becomes much more widely deployed. For instance, we have a similar thing with manufacturing for wine, for example. That was one example. We tried to do a lot wider type coverage with a lot of bandwidth. But as William said, as more video comes into play, so countries like Africa can actually skip a generation. We could see a lot more smartphones being deployed before half the cities even knew what a laptop was. Yes. We've seen something similar in India where a lot of the communities don't even know what a TV set is. They went straight to internet. volatility. So you skip a generation of technology, and by then, the back end, the consumer is commoditized and becomes cheaper.
Yeah, South Africa is by no means the only country with a significant first world and third world component service, perhaps the best example. But in comparing South Africa with the US, remember that we have 25% more people per square kilometre in South Africa on average than the US does. We are more populated than they are.
So it's an interesting element, and I didn't want to throw it in. The same study actually does a comparison to San Diego. I happen to have lived in San Diego myself, and it's only that I would estimate that the density of San Diego is probably more like Cape Town. And what's interesting there is that there the minimum is 24, I remember this, 24 acres per square kilometre to be able to do 40% of the population. Which brings me to another interesting question, and that is, we talk about age and we talk about AF, the white space. Now, the way that would work is, or the way I understand it needs to work is that it needs to be sub 1 gigabit in order to be able to take propagation of that spectrum. At the same time, you probably also want to increase power in order to get that range to work. So AH is the low power one, and AF is the one that we need more power. Those two now compete with each other. In other words, the AF requires more power to get to try and get the reach of the coverage in low density areas versus AH, which is really for the Internet of Things and is really about low power. Those two coexist.
I think so. I think, and you quite rightly say, AH is designed for Internet of Things, good penetration, to give you low bandwidth, which is what it's going to be in sub 1 gig, but enough to whereas AF is designed for a different use case. So I think you're going to find almost two overlay networks, where there's going to be an AH network irrespective. And that's going to be things like, if you think about this from a self-driving car perspective, you need cars to be able to communicate with each other, but not other data, not video data, for example, over that channel. So, AH works well for that. You get all the cars to talk to each other within a 4-kilometer radius using AH, and then use AF and AC and AX for different reasons in the automobile, for example. So I think there's going to be a place for every single one of these standards. And what we're going to find is almost like VPN, MPLS, VPN type services, where it depends on what you're doing, and that's where you decide what you want to do and what you want to implement. And of course, it'll be good to hear from the guy from Intel as to how they're going to go about supporting these multiple standards on maybe a single chipset.
Did you hear the question, Adrian?
Yes, I did. So I'm not speaking for Intel here. I was speaking about standards. But I do have some comment on this question. The other speaker was correct. The usage models of these two standards are very different. AH is unlicensed spectrum. It's probably most likely to be successful in Internet of Things applications. And although AH also has been designed for longer range, in my opinion, that's the least attractive part of it. The other thing to consider is that the regulations that AH operates under change worldwide. The really big advantage of 2.4 gigahertz is that the spectrum is now more or less the same worldwide. And this is not true for AH with Paris strictly limited in Europe, for example. The TV white space is a very different situation. There was potentially a lot of spectrum available, a huge lot of TV 11AH, but it's managed by regulation. So I don't know what the rules are in South Africa, but in the US, the rule is that there's a database, and the database records which channels are available based on the location, and those are the channels that you can use. So it has the benefit that you've got long range and available spectrum for rural communications, but it really doesn't work in cities where all of TV bands are full with either TV or wireless microphone applications. So can anybody talk to the regulation for the spectra in South Africa?
I'll hand that one to the ex-councillor.
First of all, if you're talking about TV white spaces, maybe one of the standards you should be thinking about is not 802.11, but 802.22, which is aimed specifically at TV white spaces, and is designed for significantly larger distances. In terms of TV white spaces, we currently have our second trial with TV white spaces running in Limpopo. The first one was run in Cape Town and finished 2 years ago now, I think. And that achieved 3 firsts, world firsts, one of which was that not only was it successful using adjacent channels, but it was adjacent to both analog and digital channels on both the upper and the lower side. In fact, one of the channels in Tigerbird, transmitted at Tigerbird, was between an analog and a digital channel with no interference detected. The approach taken in South Africa was the Americans started the process, the FCC started the process of TV white spaces. They started with a very conservative approach based on power contours or propagation contours. The UK has expanded on that. South Africa has used 2 databases to do it. One prepared by the Cape Town one was built by Google, and the Limpopo one was built by the CSIR. But both of the approach that we're looking towards in South Africa, obviously not speaking for ICASA here, but that I would like us to see going to is to have a fully dynamic database with every single device recorded in the database, and which requires a great deal more flexibility and processing power than the US model, for example. The US model is only is a contour based. The UK model is based on 100 by 100 meter pixels, where they calculate how many TV receivers there are in each pixel and each element, and that's run once every 24 hours. The approach that we're looking at is to run it every time a device sleeps or device tries to register. And we have some way to go with that, but we're also looking at having variable power, controllable power, depending on the signal required, and that's something that's fixed in the US model, and they're moving towards in the UK model. So in South Africa, we're trying to take the best of both the US and the UK models and come up with and do some leapfrogging. Full geotagging, full power control, and adjacent upper and lower channels. And just in terms of scale, if and when our analog to digital migration, not only television migration, not only starts but also finishes, and we then do the digital to digital migration, and we end up with the 7 multiplex model, where we have the capability to produce broadcasting up to 140 standard definition television channels on a national basis in South Africa, and I'm not going to comment on whether that's going to happen or not. The facility will exist. If that does happen, and we get to that point, we will have up to 75% of the broadcast channels will be available free, unoccupied, in any one place. Plenty of scope for TV white spaces.
Just wonder why the spectrum that is normally used to be used for cable is free, for instance, between FM 108 and 174. It's not this way, and the one from 240 or 230 cable television in South Africa. Why is it left out by itself and still battling for TV white spaces where there is spectrum available? I just want to find out exactly why those trenches are not considered in the scheme of things while we're talking about scarcity of spectrum, etc. We are pointing out 108 to 174, 230 to 470. They're not used. So why not? Because we don't have cable. In Europe, they are reserved for cable. But we don't have cable in South Africa. I mean, for action, it's a question for AH.
Not off the top of my head, no. This particular list I have only goes down to 900.
Sorry, I don't think I'm able to answer that question.
I'd take a guess at that. Like Adil said earlier, it's not a space that's used anywhere else for that same purpose. People are not developing chipsets for that frequency. They need to develop antennas for that frequency, and it just doesn't. They're going to look at where can we make the most money. They're looking at the spectrums that are used around the world, and they say, well, that's an engineering answer to that question. If I'm looking at how much it's going to cost me to service only a very small market with that antenna, I'm probably not.
That's why they will not use it for any other scale.
That's why nobody produces chips.
Yeah, because it's cable. They're not cable in Europe. I'm sure they will get first. Now, here in Africa, South Africa, I think it's Tanzania only that all has some coaxial cable. I'm looking at the reasons why you say it not
Absolutely. I mean, that makes most, like Cisco are never going to produce a piece of kit that's going to operate at that frequency. They're just not, because it's going to be such a small market.
Also, if we look at it from a global perspective, if we look at the performance standards, 2.4, 5 gig, and the lower bands that we speak about, if every country wants to kind of align so that if something gets developed in the US or Europe, we can reuse it in this space. So, if you look at cable, we may have skipped a generation of cable and gone to IPTV. Right? We had analog and digital TV, and now we're moving on to IPTV. Yes, we had satellite in between, but we could have just skipped cable. There could be a use for it later on. And if they start using it in Europe for something that we can see feasible, then that spectrum is available. But if we use it for something different, for example, in the 60 gigahertz space, China has a different iteration of 60 gigahertz. You can only use it up to 45, 49 gigahertz. So there's a standard different in the world. That means a manufacturer needs to manufacture two different radios for a single piece of equipment.
So I think just to summarize that, it's a question of economies of scale on a global basis. And then the one other thing that from an engineering perspective is that you don't have a lot of bandwidth there to play with in the first place. So it really is only quite suitable for the low power Internet of Things type of applications. And I'm not sure that, as far as I'm aware, I'm not sure. And maybe Adrian, do you know if what spectrum has been specifically targeted for the AH?
AH is 900 megahertz.
So it's not even down as low down as what the gentleman was asking.
Sigfox.
Well, I'm going to sort of defer for the moment. Willing, if you come back with that, that would be great. I want to talk about 5 gigahertz, and in particular also the 802.11ac standard. Now, the first thing that I noticed about it is that we're talking about 80 megahertz and 160 megahertz bandwidth. And sort of, if I just be an old RF engineer kind of guy, I'm going to go, oh, there's not lots of channels available. Right? And of course, there's been quite a bit of discussion around getting additional spectrum made available in 5 gigahertz. 5 gigahertz band is actually being divided into different assignments. The assignments are allocation, right? Allocation in the 5 gig between where it's license exempt and then there's spectrum for some other uses.
Allocation specifies whether it's license exempt or for some other purpose. Okay. And where it's some other purpose, then it may or may not be assigned.
So, there's been some calls to say, let's try and get more spectrum within the 5 meters. How much is that going to actually cost?
So I think if we look at where we've come from, in the 802.11a BG space, we used to have 20 megahertz wide channels. At that time, the data rates were lower, the number of devices on the network were lower, so we could easily fit that into 20 megahertz. As William said, 60-70% of the data on the internet is now video, which means
mobile data. Mobile data.
Mobile data.
Data on these things.
Yes. So, which make up a large percentage of devices connected to the internet. So when we look at those kind of stats and the spectrum that used to be available versus what is available now, we bond those channels together to give us more value. So whereas a device could connect at 11 megs or 54 megs in the past, we now see Galaxy S5s, we now see Apple iPhone 6s connecting at 600 to 800 megs. And we can just transfer a lot more data. So it makes it a lot more realistic or a lot more in line with 1 gig Ethernet. So giving that same experience whether you're on a mobile device, on a tablet, or sitting plugged into the wire. So certainly increasing the amount of channels will help us because then we can give more bandwidth to the client or we can accept more clients on it.
Are there enough channels to be able to do 80 and 60 megahertz bandwidth?
So in ETSIL or in the European standard that we fall under, when we start looking to 80 and 160 megahertz as it is today, there's not enough channels. 80 is about the limit where we can get 3 channels out of what's available. So 3 80 megahertz wide channels. If we look at 160, we can basically get 1 channel out, which is not enough because then we go back into the 2.4 megahertz. So if we can make more channels become available, that does help the situation. But also if we look at, like you said, in a sparsely deployed area, where you have 1 or 2 APs or 3 APs, then you can bond those channels, get 160 megahertz wide channel, maybe for small branches or things like that. You're getting people connected at 2.5 or 2.6 gigahertz. So they've got extremely high throughput, and you can handle the number of lines. So not necessarily saying now there is different purposes we can use 160 megahertz wide channel.
Just want to add to that from a usability perspective. If you've got an amount of data to transfer, you could do it over 160 megahertz channel in a relatively quick time. Then you're not hogging the network, and other people can use it for other things. So it's not just about I want to stream HD video and do a telepresence on a mobile device. It's about how to make the best use of the time we have because time is limited, right? You know, frequency we can play with, but we've only got a certain amount of time. There's that many people. So you transfer as much information as you can in a short amount of time, and then you give better service to everybody, which is the time slice.
And I think it comes back to one other aspect, is the consumer device, the smart device, the mobile device. When you talk about using less time on the network, that means less battery life. That's the biggest problem we have today, right? It also talks to developing different chipsets for different devices. The more radars we have in the device, it's more battery life. And when we look at 802.11ac, that's exactly the problem we try to fix. Get the data onto the network quicker, so we can save battery life, so someone else can use it.
Last question that I want to ask. So there's 802.11ac, wave 1 and wave 2. Can you take us explain that to us what that is? About 2 minutes to go.
Okay, so the reason that I see 802.11ac being split into 2 different waves, as we call it, when we take a look back at 802.11n, it took a long time for people to adopt the N standard because the standard itself wasn't ratified, consumer devices weren't developed quick enough, so we still see some legacy ABG networks out there today. So to speed up the adoption, they decided to split the standard into 2, into wave 1 and wave 2. 802.11ac wave 1 will give us up to 3 so that's what we see most commonly today, is 1.3 gigs. And then when we look at wave 2, we're looking at up to, the standard itself allows to go to 6.9 gigs, but we most likely see between 2.5 and 2.5 5 gig speed width. So it's to speed up adoption, and also they can ratify wave 1 and wave 2 at different times, so manufacturers can actually.
To address Paris's question about what happened between the FM broadcast band at 108 and the VHF television broadcast band at 174, there are 8 pages of the 2013 national frequency band plan. So there's lots of stuff. 8 full pages. I'm not going to read
One of the problems that you're describing, there's a company called Artemis that came out with a product called PISA that resolves these problems. Why hasn't this become mainstream? So there's a company in the US called Artemis. There's a product called PISA that fixes congestion at smaller time slots, smaller channels. That gives you the throughput. Says content white paper 1,000 times faster than normal LTE network. Why isn't this standard or protocol being adopted to the rest of the I'm not sure.
It's a proprietary constructive interference mechanism. They're basically trying to get enough investment to market.
But if it fixes these problems, again, why is it not something that's been supported in the mainstream?
So, Adrian, maybe you can give us a quick understanding. You say it's a proprietary standard?
I've just reported it.
I remember one meeting where Beth was debating about, you made an example of a village in Portland. Where people were almost saying, how many kilometers people should walk
you could basically create very
for people to make
tight beamforming with a very small physical bonding around an individual device and track it as it moves. That's the good side. The bad side is you need a heck of a lot of antennas to achieve that. I suspect it's one per person.
with the experience of
I'm not sure about that.
community here, we need to
So,
reconcile
I've been told it's time.
and say, not
Let's
only
just
that
do
today,
some final statement.
people, I mean, an example of saying, how do you involve code? We as a
From
business,
one side, just one
how
last
do
thing
you
to consider.
involve, Unilever,
When
we
we
as a
started off,
business,
the smart city having an AP every 300
what are the
meters.
days
If we
for
think
us
about
to
what that
think that
translates to,
the
is
only people
essentially
involved
your
are
consumer
those
devices
people
that
who
we're selling
understand,
in the network.
and
And the further you have to reach, the more data you have to push. The signal of it takes to push the data, all comes down to battery life.
and therefore
So
we need
when
the
you look at the
people
combination
who
of
run,
battery life,
you know,
throughputs, that is what the vendors like Apple and Samsung will consider. If you see the new Apple Watch, it's 2.4 gigs only, and it's specifically to preserve battery life. So we look at Wi-Fi networks, let's think about the consumer part driving what the infrastructure
we might come up with one for this year, and a year from now, I mean,
So just to, and some of the questions that you didn't answer, which is, what's happening voice over Wi-Fi and can we really run cheap access points? I think it's great to see this many standards out there, and it's allowing vendors to develop solutions that will reduce the costs of these APs, so that it's not, $100 or $200 or $300 a pop to put up an AP. And I'm personally involved in a couple of solutions where we're looking at $10, and that's something that we can take into Africa. That's something that's going to be really useful for South Africa and the rest of Africa, because then it shifts from being a commercial problem and more a distance problem. And these standards are
In Africa generally, in South Africa in particular, we rely far too much on wireless connectivity. There will always be a place for wireless connectivity. Two main reasons. One, because you're physically leaving your mobile, and the other is because you are the coverage area of someone. But we as a country need to
we can create
fix
common currency,
because that's what we need actually.
so that we have an environment whereby when we use Wi-Fi anyway,
We want 42
everyone
APs
define it
per
one
square kilometre.
in any Wi-Fi.
Every one of them has to have a
Whether
fixed
it goes to
backhaul.
Malawi, whether it goes to
You need
Zimbabwe,
fixed
whether it goes
links to make wireless work.
If you bought
mustn't think the wireless is the only solution to the problem.
in deep floor, and you are now going to go on holiday, that might not be able to be able to work. But that is why the success of different types is to not
revolutionary.
We can operate individually. We will never.
Yes, actually, I agree with the last
The best
speaker.
thing should that
I
happen
think the success
here is
of
that what I'm going to say is airtime of one Wi-Fi
infrastructure, not the
provider must work in
the
another
model
one.
in the 11
That will be the success.
an AC Wave 2 device, Ethernet X, will have some throughput something like 5 gigabits. So you have to plan for that and more. In putting down the infrastructure, you need to support the next generation of devices. So I would encourage people to look at AX throughputs and plan for that now.
Good. Thank you.
Can we thank next door's chief? Clapping for us.
Yeah.